V in minus V out, integrate 0 to T on, alright, plus negative of V out, integrate from T on to big T, and equate this to 0. Alright? So we will do this, expand out the equation. Okay? And then you end up with V out is equals to V in times phi, where your phi is a duty cycle, T on over big T. Okay? If you were to plot this relationship, what will you get? You will get this, a straight line. Okay? For a graph of V in over phi. Okay? So when phi, your duty cycle is 100%, your V in is equals to your V out. Okay? But if you were to vary your duty cycle of the switching, what will happen? Can you see that for 50% duty cycle, you get V out equals to half of V in. For 30% duty cycle, you get V out is equals to 0.3 V in. So can you see that this is a step down converter? Yes? Yes, your V out is always less than your V in. Less than or equal, depending on your duty cycle phi. Yes? You can see, right? That this is a step down converter. Okay? You can see from this graph that your V out is always less than or at most equals to your V in. Alright, so if you were to choose a switching waveform with a duty cycle which is half, 50%, you will get an output voltage that is half of your input voltage. Alright, so this is how you regulate your voltage levels, by varying the duty cycle of your switching. Okay? Alright. We have covered this, that if you vary the duty cycle, your output voltage can be set to any voltage between 0 and V in. Your output voltage will never exceed your input voltage. Okay? The output voltage is also independent of the load. Because you see in this relationship there is no load. Alright? The power delivered to the load is proportional to the current in the inductor. Okay? So when you talk about power here, it's always voltage times I, which is I of the inductor, because the load current is equals to the inductor current. But in actual fact, in any real life system, there's always some losses. Okay, but in this course, we just assume lossless. Okay? Note that this relationship is true only if current is always flowing in the inductor. What happens if current is not always flowing in the inductor? If current is not always flowing, then your flux, the net flux, will not be 0. Okay? So for this to be true, it must be in continuous mode. Alright? This is just a recap. Okay, the same waveform. Just see that I on for the supply is equals to current through the inductor. Okay, this is always in continuous mode because it's always floating above 0 ampere. Okay, there's always current in the inductor. Alright? So, if you stick with the assumption of a lossless system, the output power is equals to your input power. There's no power loss. What happens is V out times I out mean is equals to V in times I in mean. Okay? You had a relationship V out is equals to phi V in, substitute that, and you end up with V out equals to I out equals to I in over phi. Okay? Just substitute your V out with phi V in here, and then you get rid of the V in, and you end up with this relationship for your current. Okay? Just note that these are average powers because you use a VDC, a DC voltage, times a mean current. So this is average power. Alright, just take note. Okay. This is just another note. If the smoothing capacitor on the output is sufficiently large, then the output voltage is essentially constant. You understand this, right? Because in smoothing, you need if you have a big capacitor, you have a smaller ripple voltage. So it's essentially constant. The typical PWM switching frequency is usually bigger than 20 kilohertz, which is above our audible frequency, so you can't really hear it. Alright, so delta T on the capacitor will be less than 50 microseconds. You can use this, the preceding current equation to make two very important observations. First of all, the average current in the inductor is the average load current. So for example, if the power that you want to supply to your load is 100 watts, and the voltage across the load is 5 volt, and you know that current to your load is 20 ampere, that is the same current that is to your inductor. Alright, we covered this earlier on, that current to the load is equals to the current in the inductor. Okay, the second observation is the average input current is less than the output current for duty cycle less than 100%. Okay, in the linear power supply, the output current will never exceed the input current. These are just observations, alright? Okay, so if you know all this, there's a small tutorial here. Okay, you are given 4 different waveforms. Alright? What you need to do is to calculate the mean output voltage, current, and power. First of all, do you know what is mean?
Average.
Average, very good. Alright? Okay, so what's the equation for calculating average?
I think it's 1.
Alright? Is 1 over T integrate 0 to T, your VT, dt for your voltage. Okay? And for your current, you do the same, and then you multiply them to get power. Alright, here you assume 100% conversion efficiency and continuous mode operation. And that your V in is 100 volts. Okay, so let's say if you do the first one. Okay, in here, how do you calculate the duty cycle? What's your T on? 65. Okay, 65, very good. What's your period? 100. I hope you can see that this is 100, right? So your duty cycle is your on time over your period, which is 65 over 100. Okay? And you just learned that in a step-down converter, in a buck converter, your V out is equals to duty cycle times V in. Okay, very straightforward. So what is your V out now? Just take 65 over 100 times 100. Okay, in this case. Alright, so you get output voltage of 65. Alright, if what you are given here is not a current waveform. If you are given a voltage waveform and the input voltage is not given, alright, then you need to use this equation. Okay, so now you know your output voltage. Do you know your output current? You do not know, right? You're only given this waveform. From this waveform, you need to be able to calculate your average output current. Okay, how do you do this? Okay, if you can see this, I'm just doing this as an example, alright? So, you have 1 over T. Your T is 100. Okay? And you know that there's a increasing slope. Alright, what's the gradient of this slope? What's the gradient of this slope here? Okay, I hope you know this, 10 over 65. Alright, so if you take 10 over 65 times T, and integrate this from 0 to 65 and plus from 65 to 100 times, what is this slope here? Minus 10 over 35, alright? Because it's decreasing. Okay, minus 10 over 35 times t minus 65. Why? Because this is time shifted. Okay, by 65. Alright, and you need to plus 10. How do you know that this is correct? Okay, you do a check for yourself. At t is equals to 65, you put in 65 here. 65 minus 65 will give you 0, but there's a value of 10. Okay, if you put in t is equals to 100. So if 100 minus 65 is equals to 35, cancel, cancel, you get minus 10 plus 10. And you end up with 0. Alright, you have to be able to do this. Okay, given any arbitrary waveform, if they ask you for what's the rate of change, what's the peak to peak value, okay, calculate the average and calculate the root mean square, you must be able to do all this. Alright? Okay, so if you know this, now, if you integrate t, you get t squared over 2. Alright, and you substitute the corresponding values. And you get 1 over 100 times 500, which is 5 ampere. Okay, so you have just established that the output voltage is 65 volts. You also know that the output current is 5 ampere. So what is power? Just V times I. Alright, 65 times 5, and you get 325. Easy, right? Okay, you have to practice. So for the remaining questions, okay, this is a chance for you to go and practice. Any questions so far? Anything that you are not sure and you wish to ask, you can do so now, right? No? Everybody is very clear? Okay. Since we have the time now,
I can do another example.
alright, I promise to say that we will go through the tutorial exercise 1.